So now that we've had a break, let's move on and talk about Earth structure, how the Earth is structured internally, as well as plate tectonics. How do we get mountains forming, or ultimately, how do we get ocean basins forming? And this falls under the category of geological oceanography. To talk about the internal structure of the Earth, the first thing we have to do is remember that the Earth, early on in its history, was bombarded quite heavily by meteorites. The result of this was a partial heating of the Earth's surface, with the Earth partially melting, and as a result, sort of in this molten mass that consisted of the upper portion of the Earth, what we saw is that heavier elements were pulled downwards towards the center of the Earth, and lighter elements stayed towards the top. Lighter elements such as silicates, whereas iron, a heavier element, was pulled down via gravity or as a result of gravity down towards the center of the Earth. And this results in density stratification of the Earth. As a result of this density stratification, now we have a layered Earth. We have a core that consists of a solid inner nickel core and a liquid iron nickel outer core. A mantle, sort of the middle part of the Earth, which consists of really denser silicate minerals that, for you, if you're familiar with such things, minerals such as olivine. And finally, the crust, which consists of lighter silicate minerals, and the crust itself floats on that mantle. We know we have a layered Earth, and scientists have come up with theories about how this layered Earth developed. Now, how do we actually know that the Earth is layered? If you look at some of the drilling projects, a lot of drilling projects are involved with ocean drilling projects because the ocean crust, as we'll see, is thinner than continental crust, so it's less material to travel through to reach the mantle. We'll see that in 1994 we reached a depth of 12.26 kilometers in Russia. The JORDI's resolution has drilled to a maximum depth of about 2 kilometers. The Chiku, a depth to 2.1 kilometers. Hopefully deeper than that in the future. But what we see here is that these drilling ships, or these drilling rigs, have only probed about 1/500th of the radius of the Earth. So we've barely scratched the surface of the Earth, but how do we know that the internal structure of the Earth is layered? We know that internally the Earth is layered because of earthquakes, because of seismic activity. It's through earthquakes and how earthquake waves behave in the subsurface that we've been able to ascertain that the Earth does have an internal structure that is layered. So what causes an earthquake? Well, it's moving along plate boundaries, and we'll learn more about plates a little bit later on in this lecture. But what happens is we have two sections of crust that move past each other or underneath each other. What we see is that the rocks involved in this movement, especially at the location where this movement is occurring, tend to build up a lot of stress within them. The stress builds up enough over time, a lot of energy is stored, and finally that stress is released. It's almost like pulling a rubber band really tight, and then the rubber band snaps. You release that stress, and stored up energy is released in the form of what we know of as seismic waves, or the stuff that causes the Earth to shake when an earthquake occurs. The energy that is released at the epicenter of the earthquake, or the point on the Earth at which the earthquake occurs, can travel through the ground, either inside the ground or along the surface of the Earth, in a number of different types of waves. And two of the most common waves that travel through the ground are known as P waves and S waves. P for primary, S for secondary. Primary waves, they arrive first at the seismograph, and we find that these waves, they kind of travel in a compressional motion, so back and forth. It's like if you take a spring out and then a slinky and you just move it in and out. We see that these P waves can travel through both rock and liquid, or through a solid and a liquid. S wave, those are a little different. They travel in sort of a sinuous motion, so it's like if you take a rope and you kind of move it back and forth, so it looks like a snake moving across the ground surface. These secondary waves arrive secondly at a seismograph. A seismograph is used to monitor or determine when an earthquake occurs. And they are only able, because of the type of motion they have, they're only able to travel through rock. So we have these two types of waves, P waves and S waves, traveling through the interior of the Earth. One type can travel through both liquid and solid. The other can only travel through a solid. So seismic waves travel through the Earth. And because they're a wave, and we start looking at how the physics of waves and how waves act, would find that they will reflect and bend as they travel. So not only do we have the primary and secondary waves, we also have surface waves. These move along the Earth's surface. They aren't important to the story, but these will be the ones that, if people talk about looks like the Earth is moving in ripples during an earthquake, these are the surface waves. But the body waves, these are the important ones. So once again, the primary waves, we can see in the little seismograph here, or the record of the seismograph here, primary waves Compressional waves move back and forth. They arrive first. Secondary waves, that shear wave, moves more like a snake, and they arrive at the seismometer that's monitoring movement within the Earth, secondly. If you look at this diagram, or the two diagrams on the right of the slide, we see what happens as P and S waves travel through the Earth's interior. Sometimes the P wave will be traveling through and it'll encounter a liquid layer, and what this happens is it causes the layer to bend or refract. This is because we're passing from one medium, the solid rock, to a medium with a slightly different density, like the liquid rock, and this is going to cause a bending of the P waves. And somewhere on the opposite side of the Earth, or somewhere around the Earth, there's seismometer stations all around the Earth that are constantly monitoring movement in the Earth. Some of these seismometer stations will pick up the recording of the P waves, and some won't. The areas of the Earth where they don't pick up the P waves is known as the P wave shadow zone. And by looking at that shadow zone, knowing where the earthquake occurred, and knowing where we see the signature of the earthquake being recorded in seismometers, we can determine what its path was probably through the Earth's interior, but more importantly, we can determine points at which it was passing from one medium into another and bending. Now with S waves, we get something even greater happening. We have this huge S wave shadow zone, which is usually on the opposite side of the Earth from where the earthquake happened. So in this diagram here, we have the earthquake occurring at the top, or what would be, let's say, the North Pole. What happens is, S waves are not able to travel through liquid material. So that S wave, the earthquake occurs, that S wave is generated, it's traveling through the Earth's interior, but then it hits the outer core, which is liquid, it's magma. What happens then is it can't travel through it, but it sort of skims or bounces off the side, and we create this huge S wave shadow zone. So once again, by looking at where the P wave shadow zones occur, where the S wave shadow zones occur, what seismometer stations on the Earth's surface pick up the record of earthquake, which don't, scientists are able to quite definitively, to a great degree of accuracy, determine what the interior of the Earth looks like, and the fact that we have this solid inner core, liquid outer core, a mantle, and then finally the crust, sort of the thin outer layer of the Earth's surface. So by studying seismic waves generated by earthquakes, scientists are able to develop a picture of what the interior of the Earth looks like. So it looks something similar like this. You'll see a whole bunch of different words. We'll talk about what these words mean, or these terms mean, in a couple of minutes. But we have the inner and outer core, the mantle, which makes up the bulk of the interior of the Earth, and then once again this really thin outer surface, which consists of crust, which can be either oceanic crust or continental crust. We actually have two different ways that we can classify the Earth's inner structure, either based on compositional or chemical properties, or based on physical properties, and these are sometimes referred to as mechanical layers. So if we're looking at just the chemical properties, what is this crust comprised of? What are the elements within this crust, or the minerals that make up this, not crust, but make up these layers? We'd find that quite simply we have basically a three-part layering. We have the inner core, or not even the inner core, we have the core, we have the mantle, and we have the crust. And once again, we can divide the crust into either continental or oceanic. Oceanic crust is much thinner than continental crust is. Secondly, we can look at the mechanical properties, or the physical properties. So how does this rock actually behave? And this is when we see this distinction in between the inner core, which is solid, and the outer core, which is liquid. We have the mantle, and just near the top of the mantle, we have this layer called the asthenosphere, and finally the lithosphere. And the lithosphere is the outer surface of the Earth. Not exactly the crust, but behaves very similar to how the crust behaves. It's cold, very brittle. And we'll talk more about these layers in a few moments. We're not going to talk too much about the inner layers of the Earth, the core and the mantle. We might mention them briefly, but they're not the focus. What we're going to look at more is either the crust, if we're looking at compositional properties, or the lithosphere, if we're looking at physical properties of the Earth's surface. So the crust is that outermost layer of the Earth. This is what we live on, what we walk on, what we dig into. That is the crust. And we find that we can break the crust into either oceanic or continental crust. The reason why is they have a slight differing variations between them, but they're still considered crust. So oceanic crust is primarily considered comprised of a rock called basalt. And here we have pictures of basalt flows near Hawaii. The crust underneath the ocean is fairly thin. It's anywhere from 4 to 9 kilometers thick. It has a high density, which means it's heavier. It feels like it weighs more than an equally sized piece of continental crust. And finally, this is relatively young rock. This is rock that we'll find that is formed at mid-ocean bridges, and typically on the planet are less than 200 million years old. We also have continental crust, and this is typically comprised of, on average, of a rock known as a granite. This crust is thick. It can be anywhere from 25 to 75 kilometers in thickness. It's lower density than the basaltic oceanic crust. So once again, if we had two pieces, basaltic oceanic crust and granitic continental crust, same size, the basaltic crust would feel a little bit heavier than the continental crust. And this is usually older rock. We can find rocks that are as old, that comprise the continental crust, as old as 3.9 billion years old, even older. Some scientists are saying now, so rocks that were around since the beginning of the early formation of the Earth, and rocks that are forming presently. So they have a whole wide range of ages, as opposed to the oceanic crust, which is usually 200 million years old or younger. Let's take a look at the Earth's lithosphere. The Earth's lithosphere is what we call this outer surface of the Earth if we're looking at it based on physical properties. So we're not worried about the chemistry of it, but we're worried about how it behaves physically. And we see that it's very brittle, it's rigid, and it's the coolest part of the Earth's structure. The Earth's lithosphere can consist of the crust as well as a little bit of the upper part of the mantle. And it can be broken up into a series of what scientists or geologists call tectonic plates. These plates actually move around on the surface of the Earth over time. We'll talk about how their position changes over time and what causes this change in position. Basically, what they're doing is they're riding on the asthenosphere, so that section right below the crust, or it's not the crust, sorry, but the lithosphere. And the asthenosphere, we find it basically flows. It can be ductily deformed and sort of in a sort of semi-molten state. So if we take the lithospheric plates, these tectonic plates, we see that the Earth's surface is broken up into a series of sort of 7 major plates, things like the North American plate, the Eurasian plate, the Pacific plate, the South American plate, the African plate, as well as a series of numerous smaller plates. Once again, know that tectonic plates exist, but I'm not going to ask you where is the North American plate, where is the Pacific plate on a test. So geologists and geological oceanographers know that these plates have changed position over time. And what we're going to see in this slide, as well as the next 4 slides, I believe, is how these plates have moved around and changed the position of the continents and land masses throughout geological history. So we start off by looking at the late Proterozoic, about 650 million years ago. You'll see that Antarctica is sitting right on the equator. And then we'll move through looking at another period within geological time, look at the modern day world, and then finish off with looking at the future world, both 150 million to 250 million years in the future. Why or how do these tectonic plates move? And the answer is, in one sense, fairly simple. It's convection currents. So what you see is more material rises. And this more material could be like water, as we see in the pot on the left-hand side of this image, or it could be magma, as we see within the Earth's interior on the right-hand side of this image. What happens is more material rises, once again, air, water, magma. As it rises, it will push either the plates, or in the case of the water example here, wooden blocks aside. And then as that magma cools, it gets denser and it sinks back down where it warms up, becomes less dense, rises again, and you get this huge set of convection currents that are operating within the Earth's mantle. And this will result in the movement of these tectonic plates. What we'll also sometimes see is magma oozing up or coming towards the surface of the Earth at a structure known as mid-ocean ridge or mid-ocean ridge systems. This is where we have new oceanic crust being formed on the surface of the planet, albeit under the water, but it's still the Earth's surface. So at these mid-ocean ridge systems, what we see is magma coming up, and then due to convection currents, the new oceanic crust being formed, new oceanic or new lithosphere being formed here, and we see it being pushed aside away from the ridge crest, as you see that little cartoon on the right-hand side of the slide. And then eventually that material moves out towards the edges of the ocean, where then it sinks underneath the continents and creates what we call deep ocean trenches along these continental margins. The image on the bottom here is actually, you can see magma oozing out of one of these mid-ocean ridge systems. And these circle the planet and are found, as we'll see in a map later on, all over. This process where we see new oceanic crust being formed, remember the crust forms part of the lithosphere, is known as seafloor spreading. So here we have a little image. We have the mid-Atlantic ridge. So this would be sitting in this case between South America and Africa, roughly about halfway in the middle of the ocean. And we see at this point here that magma is really close to the Earth's surface. It's coming up, creating this really young crust. And then as we move out away from the mid-Atlantic ridge, which is a mid-ocean ridge system, we see that the rocks are progressively getting older and older and older. And once again, the convection currents, the movement of magma within the Earth's crust is playing a role in this. We can kind of think of this as a conveyor belt. New materials being created at the ocean ridge systems and it's carried out away towards the edges of the ocean. And this conveyor belt is really important because it explains a couple of things that we actually can, observations that we can make about the ocean. It explains why ocean basins haven't completely filled with sediment. Why, if we look at an ocean basin, eventually, we have sediment being input into it, why that eventually doesn't completely fill up with sediment. It also explains why the age of oceanic crust is always less than 200 million years old. If you look at the age of sediments, or you look at the age of rocks that make up the oceanic crust, or the sediments that sit on top of the oceanic crust, or the fossils that might be sitting on top of the oceanic crust, we'll never find any that are really older than 200 million years old. And that's because this conveyor belt motion, the rising of the new and creation of new crests of the mid-Atlantic ridge system, and then the movement off towards the edge of the ocean, result in the destruction of the ocean crust at roughly about 200 million years since it was initially formed. This image shows some sediment on the right that's made up of a whole bunch of different biological microfossils, and a little cartoon that just sort of illustrates that, why we have this ocean that's not filled with sediment. So none of us can sit around for 200 million years and watch the Earth's crust move from a mid-Atlantic ridge system setting, for example, towards the edge of the Atlantic Ocean basin. So how do we know that this is happening? And we know it through something called paleomagnetism. So to talk about that, we have to go back to the Earth and the internal structure of the Earth once again. We know that the core, the inner and outer core, are made up of nickel and iron. Basically, what we see because of this, the Earth acts as a big magnet. And if we could actually have a way of physically seeing them, we'd see that the Earth has a magnetosphere, something similar to the atmosphere, but it's this invisible sphere that surrounds the Earth. We have these magnetic force lines that point into the North Pole and point out the South Pole, and it actually makes the Earth into a great big bar magnet with a positive end and a negative end. So what does paleomagnetism have to do with the fact that we know that we have new crusts being formed at mid-ocean ridge systems, and that crust only lasts for about 200 million years, and that we have these big convection currents acting within the Earth's mantle? Well, if we look at magma, and we look at some of the components within magma which cools to form rocks, we'll see that there are some minerals that are magnetic. In particular, we have a mineral called magnetite, and that's a picture of magnetite on the left-hand side. There's sort of that black pyramidal shape. As the lava cools, or as the magma cools, or even as sediments are deposited that contain magnetite, what happens is these minerals, or magnetite, will align in the direction of the Earth's magnetic field. Magnetite is a big component, or not a big component, but it's plays a major role. We see a lot of it in basaltic lava and ocean sediments. So as the basaltic crust is being formed, we see any magnetite crystals that might be crystallizing out of the magma that's forming that basaltic crust become aligned with the direction of the Earth's magnetic field. And we see that sort of in the image to the right. In this case here, we're looking at sediments, but you can get the sense that everything that is magnetic becomes aligned in a certain direction. They all sort of travel or have this general trend within the direction of the Earth's magnetic field. Not only do we have minerals that will align with the direction of the Earth's magnetic field, but we also have this other interesting phenomena, and that's the fact that the Earth's magnetic pole will flip throughout geological time. There will be times, and we're experiencing it right now, where our magnetic pole is north, the North Pole. We know that compasses point to the north, but there have been times in the geological past where the magnetic pole is actually the South Pole. So the North and South Poles swap positions. And we actually can have created a geological record of times when we see the North Pole being magnetic and the South Pole being magnetic. The most recent one was about 30,000 years ago. Some scientists say that we're overdue for a magnetic flip. Currently, it's not something I would stay awake worrying about, but we're sort of in that phase that maybe we should be flipping back over to magnetic South Pole. So we know that minerals align in the direction of the magnetic North Pole. We know that, or the magnetic pole, we know that at times during the Earth's history, the North Pole has been magnetic. Other times the South Pole has been magnetic, which means that we should in the rock record, and remember rocks have been crystallizing, forming over hundreds of millions of years, we should see times where these minerals are aligned pointing towards the North Pole, and other periods of time when these minerals are pointing towards the South Pole. So these reverse when the South Pole is magnetic, or normal when the North Pole is magnetic, polarities are recorded in the rocks and sediments of the ocean floor, and particularly the basaltic magmas. What happens then is if we use a ship pulling something called a magnetometer, which measures or records the magnetic signature within the rocks, what we see is this pattern of periods of normal polarity within the rocks and periods of reverse polarity. Obviously, if we get right at the middle of the mid-ocean ridge, we know we're in an episode of normal polarity. We'll see that. But then as we move out away from the mid-ocean ridge, and actually you'll see that it's mirrored on both sides of the mid-ocean ridge, it's symmetrical, we'll experience episodes of reverse polarity as well as episodes of normal polarity. To continue the story on how we prove that we have seafloor spreading happening, the creation of new crust, is that the basalt, actually, we can determine the age of it radioactively. We can see certain elements, how long they decay radioactively over time. They move from a mother element to a daughter product here. And from that, we can look at how old the rock is, and we can look and see if it's a normal polarity signature or a reverse polarity signature. And we can actually come up with sort of what we call a stratigraphic section. This is what we see on the right-hand side of the image here, where we see this vertical column, and it represents periods of normal polarity as well as reverse polarity. And we have a time scale associated with it as well. So now if we go back to the Mid-Atlantic Ridge, and here's a great image of the Mid-Atlantic Ridge near Iceland, we can see the North American plate to the left, the European plate to the right. We'll start to get a sense of what's going on and how we can prove that this seafloor spreading is occurring. So we take a ship pulling a magnetometer and we travel across the mid-oceanic ridge. In this case here, we're looking at the Mid-Atlantic Ridge, not too far off of Iceland. And what we'll see is we'll get a symmetrical pattern. So you start the Mid-Atlantic Ridge, and as you work out from either way from that ridge, we'll start to see, as I said, symmetrical or mirror image. We can assign dates to that as well. And we can see that, for example, if we look at the band of blue here, which would be a reversed field of magnetic polarity, what we see is that it is occurring at roughly the same time, and it's at roughly the equal spacing and size on either side of the Mid-Atlantic Ridge. Look at the orange and the yellow strips as well. There's a few variations, but we start to get a sense that there's something forming at the middle of the Mid-Atlantic Ridge and then moving out on either side of it at roughly the same speed and of the same sort of chemical or physical makeup. So with all of this, looking at the age of the basalt rocks, determining how old they are, looking at the magnetic anomalies, are they normal magnetic polarity or reverse magnetic polarity associated with them, what we do is we discover two things important that occurs at these mid-ocean ridge systems that kind of help prove that what we've been talking about, that this is where new ocean crust is being formed. What scientists, what geologists and oceanographers have discovered as a result of this work, looking at paleomagnetism and the age of the rocks, is that the oldest oceanic crust is only about 200 million years old. So here's a map. Land is in the brown. All the different colors that we see in the oceans refer to different ages. And we see that sort of on the edges of the ocean basins, we get that light bluish color, either a sort of more of a cyan or the pale blue. And we find that it's roughly about 144 to 161 million years old. Once again, MA is short form for millions of years.